everybody. Thank you so much for being here today for the July edition of Lunch a la Carte, a lunch and learn session that the CART Fund sponsors so that you can have a chance to hear from some of our researchers directly and to ask them questions and to learn more about their research. And we have a couple of quick announcements for you before we move into today's speaker. Just wanted to remind you that it is still an opportunity for you to join the Roger Ackerman Circle. If you would like to become a recurring donor to the CART Fund, you can do that through our donor portal. I will put that link in the chat a little bit later as well, but it is mycartfund.org. And we appreciate the nearly 140 of you who have done that already. It is certainly making a big impact and a big difference in our fundraising efforts. As you know, July 1 is the beginning of our new fiscal year, and we are excited to be moving forward and breaking new records, which we did this past year when President Rod took over as president of our board of directors in July of last year. He set a very lofty goal for us to raise $2 million in a year by the time that his 2 years is over, and we did it in the first year. So we are thrilled that he has set those lofty goals for us, but he says that we cannot rest on our laurels. We must continue to work hard, and we appreciate what each of you do that help us to make those goals possible, and of course to help us create lasting change, because we know that as Rotarians we are creating hope in the world, and we all on this call have a hope that we will find a prevention, treatment, or cure for Alzheimer's, and we are excited that you are a part of our team. All of the Zoom links for these meetings and all of the CART meetings are now posted on the calendar page of our website. So if you can't find a last minute link, you can easily go to the website and click on the calendar, and one click from there will get you into these calls. Lots of activities coming up both locally and online, and we hope that you will continue to join us as often as you can. One final shout out, if you would follow us on our social media. We are on Twitter, we are on Facebook, and we are on YouTube, where we record and save all of these videos. Again, I say thank you for your time today. Thank you for your time every day, what you do to support us. And at this point, I'm going to turn it over to immediate past district governor from 7670, Tammy Mosteller, to introduce our speaker.
Thank you so much, Tiffany. What an honor it is to introduce Dr. Murphy. He is quite the interesting Irishman. Dr. Murphy has worked as a researcher in the area of aging and neurodegenerative disease for more than 30 years. He received his master's degree in psychology and a PhD in neuroscience, both from the University of Toronto, and was a postdoctoral fellow in Dr. Todd Gold's lab at the Mayo Clinic, who was also a CART recipient. He joined the UK facility and the Sanders Brown Center on Aging. And in 2005, Dr. Murphy's lab studies the production of the amyloid B peptide, the regulation of these processes, and how the peptide ultimately forms pathology in the brains of the Alzheimer's disease patients. He has a long-standing interest in models of the disease, mainly genetically modified mice, which are invaluable tools for both furthering an understanding of the disease and for the developing therapies. Several of the mouse models that Dr. Murphy has been involved with from the developmental stage onwards as well are well known and widely used in the Alzheimer's disease field. His lab has received funding from the Alzheimer's Association, the American Heart Association, CART, the Kentucky Science and Engineering Foundation, the American Federation for Aging Research, and Bright Focus Foundation, and also 5 different NIH institutes. In 2010, Dr. Murphy was honored by the receipt of the Thomas Masiag Award from NIH for exemplifying research excellence and innovation, and for the mentorship of new scientists. He has been named to the UK College of Education's A Teacher Who Made a Difference. He's listed in 6 separate years he was awarded that. And in 2013, he was honored by the UK College of Medicine with the Abraham Flexner Master Educator Award for Outstanding Teacher and Mentorship. That's quite an accomplishment. In 2019, he was awarded the Associate Director of Education for the Sanders Brown Center on Aging. And then in 2022, he was appointed as co-director of the NIH-funded National Resource Center for Supporting Research Excellence, a unique effort designed to build and sustain research capacity at small institutions that have traditionally received minimal support, such as those serving minority and first-generation students. He has authored manuscripts in Science, Nature, Nature Medicine, Journal of Biological Chemistry, Annals of Neurology, Journal of Neuroscience, and the American Journal of Pathology. He has written influential opinion pieces for publications such as the New England Journal of Medicine and has been interviewed by multiple news outlets, including Wall Street Journal. Today, he's going to tell you about investigations in his lab that started with a CART award in 2010 and is currently supported by a multi-year grant from the National Institute on Aging. Thank you, Dr. Michael Murphy.
Yep, thank you so much. Yeah, it's great. It's great to be here. And yeah, I do, even though my first name is Michael, I go by Paul. It's because, as you mentioned, I'm Irish, and my father, who passed away some years ago, he was Michael also, and everyone called him Mickey. So when I was young, what everyone started doing, they started calling me Wee Mickey. So my mother hated that. So I'm always thankful for her deciding to call me by my middle name and not letting me be Wee Mickey for the rest of my life, because my dad got to be Big Mickey. So it's like, oh, look, it's Big Mickey and Wee Mickey. So I'm glad to not be Wee Mickey. So, but I do answer to Michael too. So, but you'll see I put on my Zoom name and I'm Paul. So what I'm going to focus on today is something that's very topical. So this is kind of both directly and indirectly related to my main research program. So what I want to cover today is where we're going in therapies for AD and where we stand now, because there's been a lot in the news recently, especially last week, since lecanemab got approved last Thursday, which is a tremendous step forward. I'm going to tell you a little bit about why. My lab has worked on different immunotherapy approaches for years, along with a lot of other people in the AD field. So it's kind of this whole recent advances that we've been getting are really a massive national and international team effort that people have been working in this area on for probably 20 odd years. So what we did with our CART grant back in 2010, 2011, we used that to develop a new mouse line. And these mouse lines have been incredibly valuable for developing therapies, and they've been really instrumental. And I'll tell you a little bit more about it at the end if we have time. But what I really wanted to focus on was where we were going in terms of therapeutic development and why it's important. So I always put this up because sometimes people ask, do I have any financial entanglements with anything? I do not. I try very hard to keep financial stuff separate from my research things. So I'm very proud of that. So what we generally now have is our lab is supported by several different NIH grants. So that's our main source of funding. And we do have some internal funding too, but mostly it's federal. So I'm not getting any money from any pharmaceutical companies or anything like that. So I'm not promoting a therapy that everyone should buy or anything like that. So I know you all are familiar a little bit with Alzheimer's disease. So I'm not going to spend a lot of time talking about the backstory, just give you enough to kind of ground you in where I'm going with this. So the AD brain basically is, by the time you get to late stage Alzheimer's disease, there really is quite a lot of damage. A colleague of mine once said to me that when you look at later stage AD, it's almost like a bomb has went off in your brain. There's a tremendous amount of cell loss and damage. And no matter where you look, you can find evidence of that fallout. But what we don't talk about so much, but it's pretty commonly known these days anyway, is that, it's a very common disease. There are about 6.5 million people in the US with Alzheimer's now, and that number keeps going up. And as I'm sure you've all heard plenty of times, and as for all of us that are in our 50s and older, we know that generally our population is getting older, right? Just as our demographics are just shifting in the 2030s and 2040s, there's going to be a lot more proportionally older Americans in our population than we've had in the past. So Alzheimer's is going to be a much more significant problem and a more significant burden on our public health system, as well as on caregivers and family members going forward. So it's going to get worse. One thing that we don't talk too much about is that the majority of Alzheimer's patients are actually women. And a lot of our research these days in my lab is focused on sex differences in Alzheimer's disease, and if we can figure out why women are disproportionately affected compared to men. So our two main aspects or hallmarks of Alzheimer's disease pathology in the brain are amyloid plaques, which are deposits of this A-beta peptide, which you probably have heard lots about at this point. It's one of our most discussed elements of the disease. And tangles. And tangles are made up of this intracellular protein called tau, which is important for stability of the cellular cytoskeleton. And the main distinction between these two, and obviously I'm glossing over a lot of subtleties here, is that the amyloid pathology is found outside neurons in the brain. So these plaques are extracellular deposits of the peptide. and you get a lot of inflammation from that. So there's a lot of inflammation fallout and a lot of cell death that's associated with those amyloid deposits. And you have intracellular pathology of the tangles. So the tangles are found inside the cells and the plaques are found outside the cells in the brain. But they both occur together. You have to have both of these pathologies in the brain, as well as a very characteristic pattern of neurodegeneration to have Alzheimer's disease. Otherwise, it's something else. So that peptide comes from this precursor protein called APP. And most of the models that we made in the past, and pretty much all AD models, have something to do with this amyloid precursor protein. So the one we made that was sponsored by a CART grant back in 2010 was also an APP model. So what we did with this one is we introduced mutations that cause Alzheimer's disease in people into the mouse. Because mice don't get Alzheimer's disease. Nothing else, actually no other species gets Alzheimer's disease other than humans. It's a human-specific disease. What you see in people is that precursor protein is affected by a variety of different things. So just the aging process itself, a variety of very rare but really interesting pathogenic mutations that guarantee you'll get Alzheimer's disease. A lot of genetic modifiers that come into play later. So there's a lot of age-associated genetic risk factors that you may have heard about. Probably the best known of these is apolipoprotein E4, which if you go in any Alzheimer's disease trial or clinical therapy, they always screen you for E4. I'll come back to that a little bit later. And a lot of things in diet and metabolism. One of the things that we tell people when we do public outreach and talk about what you can do to prevent Alzheimer's disease is, and it always sounds like such a lame thing to tell people, but your best defense against Alzheimer's disease is being healthy. So just getting good exercise, both mental and physical exercise, and eating well, keeping the amount of fat lower in your diet, not eating too much, all of the things that you would basically tell anyone anyway about just maintaining good health works to prevent Alzheimer's disease. So Alzheimer's disease, one way of thinking about it is a consequence of a lifelong wear on your brain just due to a series of just your normal life choices, right? And one of the best ways to reduce risk is to be healthier in general. So all of these things modify how that precursor protein is handled in the brain. And A beta gets cut out of that precursor protein. And it's initially one tiny little peptide. And this actually happens not just in your brain, but all through your body. It just, for whatever reason, it tends to accumulate in the brain. So over time, it forms these higher structures. It's kind of sticky, so it sticks to itself and it forms bigger and bigger pieces. So those are somewhat soluble initially. But with time, they start to kind of become larger, clumpier deposits and aggregates in the brain. And that's how you get these plaques. And somewhere along that process, in addition to the plaques being formed, it influences the formation of those tangles inside the cells. And together, all of these things together, the toxicity of that peptide on its own, the plaques and their associated inflammation, and the tangles inside the cells, all of those things are acting to cause the neurodegeneration or the pattern of neurodegeneration that leads to Alzheimer's disease. Now, how A beta is related to AD is really complicated, and I struggle a lot with trying to get this down, kind of boil down to the nitty-gritty so it can make it clear for everyone. All through your body, and even with normal aging, there are these two enzymes called beta secretase and gamma secretase. They're cutting that precursor protein. And the A beta region is that little red bar that I'm showing there, partially stuck in the cell membrane. So a little bit of A beta gets made in your brain all the time. And this is happening from the time you're born all the way through your entire life. And normally, that peptide is getting cleared out of your brain. One of the things that we study in our lab now is how sleep relates to AD. And I know we can all relate to sleep and getting a good night's sleep or not. But it turns out that A beta is cleared from your brain during sleep. So at different times of day, there's more A beta in your brain. It goes up and down through a daily cycle, right? It's affected by things like jet lag. So that changes with age. It may be more affected in women that way than it is in men, which is really fascinating. So all of that, so when you're asleep at night and when you're in REM sleep in particular, that A beta gets cleared from the brain. Now, what happens in Alzheimer's disease is a lot of these things go awry. So in AD, what you have is more beta secretase activity and a little bit altered gamma secretase. So you have more of these two enzymes working together. And that gives you both that increase in beta secretase and a change in gamma secretase, gives you more of that A beta peptide getting made in the brain. And then in addition to more being made, things like changes in your sleep cycle and just other aging related processes slow the clearance from the brain as well. So because you have more of it getting made and it's not getting taken out of the brain as fast, it starts to build up. So you think about that as like if you're generating more garbage and then no one's coming to pick up the trash, it's going to start to build up. There's going to be lots and lots of it after a while. That's really what's happening in general, right? Now, why we believe that A beta causes AD is a really long argument. And this is where I think as AD researchers, we have to work harder to communicate this, because this is really the basis of how we study the disease and how we develop our therapies. So there's really 5 key things here, and this is kind of how I've boiled this down. There are the mutations that cause A beta to increase or that alter A beta. So although these are rare, they tell us a lot about the disease. Whenever you have any of these inherited mutations that change A beta to make it more prone to forming these structures in the brain, or there just being more of it getting made, those individuals always get Alzheimer's disease. So it guarantees you to get Alzheimer's disease. And even though the mutation gives you more A beta, it leads to plaques and tangles and neuronal loss. So even though the mutation causes more A beta, you see the tangles as well. Now, if you have mutations in tau, that's the thing that makes up those tangles in the cells, that causes a different disease entirely. So that disease is called frontotemporal dementia. And that gives you those neurofibrillary tangles made up of tau and the neuronal loss, but there's no plaques. So that's telling you that those tangles happen separately from the A beta pathology. And you can put these in order. If you add A beta to our mutant mice that have a tau mutation, that amyloid increases the tangle pathology, makes it occur faster and causes more neuronal loss. That's telling you that that A beta is pushing or driving those tangles to be formed in the brain. And if you take the tau away, that doesn't have any effect on A beta at all. So it's telling you that the tau pathology is happening after the A beta pathology. And if you look at just A beta on its own, even huge amounts in humans or in mice even, there really isn't all that much pathology with it other than the deposits of A beta. If you don't have the tangle pathology going with it, you don't get neuronal loss and disease. And what I think is really the kicker that's come into play in the last 20 years or so, now we've got really good imaging technology. We can see that the amyloid pathology shows up in the brain before any of the tangle pathology does. So we're getting much better at this detection. So now we can really put these things in order. And we know that A beta and AD, there's really a long clinical phase here, a long preclinical phase. So we know that you have amyloid pathology in your brain for about 20 years or so before you actually start to have clinical symptoms. So you look in your 50s or so, you can see most people have a significant amount of amyloid, right? Or at least some that you can detect. And it takes a long time for it to get up to a level where it's actually causing a lot of harm. So that A beta pathology, you can see the red line here, it's showing up before everything else. So the orangey line at the top, which is showing you how much your neurons, you can see that the A beta is around for a long time and slowly accumulating before the neuronal loss starts to happen. The tangle pathology shows up after that. And in between there, you have a lot of inflammation that's associated with the plaques. And that sort of chronic inflammation is another thing that drives a lot of the damage in the brain. But it's only when you start to lose those neurons when the memory loss starts to show up, right? So that gives us actually not only really useful temporal sequence of events, but that shows us where we can intervene, right? I mean, if you go really early in the process, that gives you a lot of hope to slow the disease down or prevent it. It's much harder when you get later in the disease, and we'll talk about that a little bit at the end. So as you all know, the incidence of AD is increasing with age. It goes up to about 5% by age 65 and then about doubles at each decade. Interestingly enough, once you go into your 90s, if you make it that far, the risk starts to go down, but you get a lot of other health concerns when you get into your 90s. So it's not all fun and games at that stage. But you do lose some of the AD risk, and that's actually interesting. And there's a lot of reasons why that happens. But one of the things I think that gets lost in the shuffle a lot is when we're talking about how we go about developing therapies and how we think about this, is that because there is it's an age-related disease and develops very slowly over time, we don't need to completely cure it to make a huge difference. And by that, I mean, if you're thinking about AD as just being a pattern of neuronal loss as being driven by these different elements of pathology that occurs in an age-related way, hopefully this will not be a surprise to anyone here, but eventually everyone will pass away. So if you slow the disease down enough to where it would not be a risk until, for example, it's only a risk in people that are over 100, then it's not going to be as much of a public health problem because you'll be dealing with it at a much earlier age and it won't be quite so significant. So you can see what I mean by that. From the time when people have the onset of AD symptoms till the average age of when they would require full-time care, it's maybe in the neighborhood of about 5 years or so. There's a little bit of variability in there depending on the diagnosis. But if that's our normal situation, if you think about what would happen if we had a partially effective therapy that could just slow down the disease progression, so kind of bending the curve, if you will. So if you have just a partially effective therapy that can slow the disease down even a little bit, then by the time the person passes away, they haven't declined enough to require full-time care. So it's a huge advance in terms of how we can handle the disease. And if you can couple that slowing of the disease process down by going a little bit further back, so you can actually move your detection back, for example, by looking at markers in cerebral spinal fluid or just PET scans, or even a blood test for AD, which is still possible. If you can detect that even earlier and you have a therapy that doesn't completely cure the disease, but just slows it enough, it then doesn't become a problem at all, right? Because everyone will eventually pass away. It almost sounds weird when I say it, like it's like a grim, morbid thing, but it's true. If you slow down something like that enough, it will no longer be a problem. So given all this, it should be possible to treat AD. And for like the last 20 or so years, I mean, the way I couch this to patient groups when I talk to them about it is that we thought back in the late 90s, when we had found a lot of the molecular mechanisms that were involved in making A beta in the brain, that we would have AD cured in about 10 years. And it turned out to not be that. And there are a lot of reasons why that is. And some of it was just how we were thinking about the disease was wrong. But if you think about the way I've laid out the disease process for you, it should be possible to treat it. If A beta is really way upstream of everything in the disease and we can target it, you should be able to clear a lot of the pathology in the brain. So where we stood in 2018, so this is now we're very recently, so I'm fast forwarding through a bunch of stuff. We actually were kind of in a bad place then in 2018 as a field. This is from the editorial I wrote in New England Journal of Medicine back then, when we were talking about why we had so many failed clinical trials and where we might be going. So in general, in 2018, what we were thinking of is that, well, maybe we're just not going early enough and that we shouldn't be treating people later in the disease, that we should be trying early, but that just didn't seem to be a very satisfying answer. And we were starting to have these doubts of whether we were maybe wrong about amyloid, and maybe it wasn't the key thing that was driving the disease after all, and that we were completely off base and we just were not using the right mouse models, because we were really reliant on those mouse models that we made. As there, you can't test these new drugs in humans until you have some evidence that they work in some other system, like a mouse. So, and maybe because we might have been wrong about amyloid, that maybe we should be looking more at other targets. And that's always worth doing too, because, there is a lot of tangle pathology in Alzheimer's disease. And we know that those tangles are driving a lot of that cell loss later on. So targeting tau is really a significant thing that we need to be working on. So a lot of this stuff really started to worry us, so especially since we've had so many failures. There's actually been about 300 different AD-related trials, and probably 25 or 30 or so really serious stage 3 clinical trials. And over these dozens of failed trials, or phase 3 clinical trials, we have learned a lot. I mean, we've tried a lot of different strategies here. Many of these therapies have targeted A beta have worked all their way through the clinical trials, from safety trials through dosing and efficacy trials at the end. And the drugs that block the enzymes that make amyloid, we've had things that clear amyloid, things that block aggregation, things that inhibit inflammation. We've tried all of these things. And one thing that we have had up until about very recently, in the last couple of years, the ones that have always been the most promising have been the immunotherapies. And we're going to talk a lot about that because that's really what's been in the news a lot recently. So if you just look at a general table here of different therapies, you see a lot of them are immunotherapy based. I'm not going to walk you through this table. It's tedious, so you don't need to worry about that. This is just purely like a list of failure. But right down at the very bottom of that, there you can see aducanumab, which is right at the very bottom at 2020. And aducanumab was extremely controversial. The reason being is that it was handled very poorly by the FDA. And let me walk you first through an analogy about why we're really worried about this, or why we have been worried about this in the past. This is a really interesting analogy that I wish was mine. It's not. It was in a paper by Knudsen back in 2014. There's a link there at the bottom that you can follow if you want to read it. It's called the airbags and Alzheimer's disease analogy. So, and I've modified it a bit, so it does have my own little touches in here. So if you imagine a scenario where aliens who don't know very much about Earth or humans are studying car accidents. So what they see looking at us from space is that when you look at an intact car, the airbags are packed away, right? And then when the car is in an accident, they're out, they're deployed. And then they start studying this in more detail, and they find that there are these rare cases when a manufacturing error causes the airbag to deploy erroneously when you're driving, hits you in the face, and then you have a car accident, right? Not surprisingly, that's going to be pretty distracting, right? So the aliens say, we know there by looking at this evidence that airbags have to cause car accidents. They can even prove that, right? If they actually introduce defects into people's cars and force the airbag to deploy, it causes an accident. So like, oh, look, see, if we cause the airbag to hit someone in the face while they're driving, it causes an accident. So therefore, we know that they cause accidents. Now, because they don't know what an airbag is supposed to be for, this all seems very logical to them, right? So they decide to help out us poor, stupid humans by using an airbag inhibitor, by beaming down some software from space that will prevent the problem by preventing airbags from working. And then they find out, to their amazement, that the overall number of traffic accidents doesn't change. In fact, fatalities go up. Although this leaves the aliens really confused and they don't understand what's going on, to us, it makes perfect sense, right? Because that's not what the airbags are doing. They're not supposed to do that, right? They're supposed to prevent injury after an accident. They have nothing to do with the accident. Now, see what I mean by this is we're taking this analogy to its conclusion. If you imagine the AD inside of your brain like a car wreck, right? So that car wreck is actually a catastrophic incident that triggers a whole bunch of traumatic injury in the brain. So if you go about making changes to these things that went wrong and caused that, it didn't really cause that wreck to begin with, it's kind of analogous to if you think about your brakes being defective, fixing the brakes after you've had the car accident isn't really going to help you anymore, right? So because we don't know a lot about what that A beta peptide does in the brain, or what the APP protein does, the thing that A beta comes from actually does. It's surprisingly, we know so little about what that actually does in the brain. We could be totally off base by we're not targeting the right thing. Maybe we should be targeting some other element of the process. So this is the sort of thing that's been nagging at people for a long time, that maybe this whole target is wrong. And those mutations that we're using to model the disease in mice is actually just something like analogous to this defective airbag deployment. And A beta is kind of the airbag going off in your brain, right? And it's really something else that we should be looking at. And this is really where we were in 2019. And hopefully this will not be the only time I ever get to be on the front page of the Wall Street Journal. But if you're thinking about where we're going wrong here, is that if we have so much effort put into these, it takes a couple of $100 million to run a phase 3 trial through to conclusion. So it's not a cheap thing to do. You think if you keep having all of these failures, you won't really have much incentive for pharmaceutical companies to continue to develop drugs in this area. So, I mean, this was all very depressing. This was back after the aducanumab trial kind of washed out, or appeared to wash out, back in 2019. And this is where I give you my little halfway point Rivet, to give you a little bit of time to take a breath and to cheer you up, because Rivet has a lovely smile. I have 4 cats and 2 guinea pigs, and Rivet's my current favorite. He's very cuddly. So he's here just to cheer you up. Now, let me explain why we think these things have gone wrong and why they've gone right. So this is an example of a couple of the antibodies that a couple of different companies developed, gantenerumab and solanezumab. Don't worry about pronouncing them too much, they're a mouthful. There's a reason why they make these things ridiculous. It has to do with people who make generic drugs not being able to rhyme them with the original, believe it or not. So if you look at how these things work or don't work, generally, if you look at all of these failed trials are kind of similar. If you look at cognitive function and how it changes in people with the disease when they're on the drug, they generally don't change very much. So you don't need to worry about the details of these individual things. These are just different measures of people's rates of cognitive decline with Alzheimer's disease, whether they're on the placebo or on one of the monoclonal antibodies. But if you have a good drug, it does actually do what we call have good target engagement. So it actually reduces amyloid in the brain quite a lot. And what's really fascinating about them too, is they also reduce tau as well, which is about what you would expect, right? If A beta pathology is upstream of that tangle pathology. So you remove the A beta and then you remove the tau. But yet they didn't seem to work. So you wonder what's going wrong with our ideas and why are our models not working right? Now, around this time when we were kind of fretting over what we've been doing wrong, the FDA kind of surprised everyone by doing this emergency accelerated approval for aducanumab. And this is under the brand name Aduhelm, right? And it was originally pitched as being selling for about $50,000 a year, which is quite expensive given how weak the data were. And this created a huge controversy. So when this came out, and this was back in around this time in 2021, so a couple of years ago, and it created such a huge fallout, was that we had a lot of people resign from the FDA's advisory committee. People started to be concerned that we were just full of crap and we were not really thinking about the disease the right way. I get these editorials and things like Scientific American saying that, you know, our whole hypothesis of amyloid and Alzheimer's disease is just too big to fail. And we're just like wasting our time, just spinning our wheels doing this. But as it turns out, I mean, one of the reasons why this was controversial is because the effects for aducanumab were really weak. So even though it worked super well in our mouse models and in the early trials in AD patients, it really didn't slow the disease very much. And actually, the big controversy was there were two actual wings of this trial. They were called Engage and Emerge. And it actually, the drug only worked in one of them. And there were some concerns about how they'd switch their method halfway through the trial and things like that. So there was a lot of doubt over whether this was really a real thing. And because it was so expensive, you had things like the VA refused to use it to treat veterans because it said it's just too much money for so little efficacy. So then we're just kind of saying, well, you know, this is all fine. The FDA said it was okay because it did work to clear amyloid from the brain. So they said, well, even though it's really expensive and there's no evidence that it helped to treat people with the disease, maybe eventually it will work, right? That is not a very satisfying place to be. But we still actually did make a lot of progress. And this was very recent. This is in the last year or two. Now, so lecanemab, that's a drug also from the same company that made aducanumab. So it's a different monoclonal antibody. That company, Biogen, actually showed really, really, really strong data from lecanemab last year. And that led to an early approval, an accelerated approval for lecanemab in January of this year. Now, for those of you who've been following the news, they went for full FDA approval very recently. Now, in the interim, before we got to the full FDA approval for lecanemab last Thursday, is extremely recent. Another drug, so Eli Lilly announced a similar but slightly different version called donanemab. So it said these things are all a mouthful. Back in May, and it actually looks much better than lecanemab in terms of efficacy. And so they're going to announce their results next week at the Alzheimer's Association conference in Amsterdam. And everyone is anticipating that they've already filed for approval and they're almost certainly going to get it. Now, let me show you why these things work and tell you where we're going from here and why this is so interesting. This is the effect that you see in lecanemab. So it's not a huge difference, but when you have over 18 months, you'll see that it slows down the disease. So it buys people maybe about 6 months of time. So it doesn't sound like a lot, but it is. It does make quite a bit of difference. And one of the caveats that you need to keep in mind with this is that going earlier in the disease with something like this will actually lead to an even larger benefit. So slowing that disease down by 6 months in someone that already has Alzheimer's disease is a pretty big advance considering that we haven't had anything before. And now by moving back even further, because we're really good at detecting early stage disease now, that could probably really, really slow the disease down significantly. And the other thing is it's incredibly effective at removing amyloid from the brain. And one of the things that's interesting here is how quickly it takes the amyloid out of the brain. You can see quite a big drop after about 6 months, and really about half of it is gone by about a year. And that time course is really important. I'll come back to that in a second when I talk about some of the other ones. There's some interesting subgroup differences. You remember earlier on, I said that a lot of individuals who get late stage Alzheimer's disease have apolipoprotein E4 alleles, so they have a genetic risk factor for it. It doesn't seem to be all that effective in individuals that are carrying the ApoE4 allele. So that's a concern. It might be that a lot of the people, somewhere in the vicinity of maybe 20% of individuals get Alzheimer's disease in their late 80s and 90s, have one or two alleles of the ApoE4 protein. So the fact that the drug appears to be less effective in those individuals is some cause for concern. So there's room we can do better there. And the other thing that we haven't talked about too much is this difference in sex as well. And it turns out that most of the efficacy appears to be in the men that were in the trial. And it didn't seem to work nearly as well in women. And this is something that as a field, we've been paying much more attention to in recent years, that in addition to being a lot of differences between how men and women respond to different drugs, is that there's already more AD cases there are women compared to men. And if we can't address that difference, it's a big problem. Right? That's not necessarily going to hold up for all of these drugs, but it is cause for concern. And part of it may be that women tend to have such a more amyloid pathology in the brain to begin with than men do when they come down with Alzheimer's disease. It might just be harder to clear. So it may just mean going earlier in women than in men to be effective, to get the same level of efficacy. The other concern that we have with the monoclonal antibody therapies is the safety concern. And this is what you've seen in a lot of the editorials or news if you've been following this. One of the things you see with all of these monoclonal antibodies is this thing called ARIA. So there's these amyloid-related imaging abnormalities. So this is really very simple. It's just a swelling of the brain or some hemorrhaging associated with it. And in most of the cases, and this is quite common with these drugs, so it's about 1 in 5. But most of the cases, nearly all of them, are actually asymptomatic and don't seem to be cause for concern. But a small number of them can become very serious. And there's some evidence that there have been a few deaths in the clinical trial that were related to these. So that it's not like these drugs are totally benign. They do have some significant risk associated with them. But I think if you're trying to think about whether these are beneficial or whether the benefit of risk or risk reward benefit is worth it, one of the ways that I think is informative to consider these is that they're kind of in a way similar to something like a lot of chemotherapeutics for cancer, is that there's going to be some risk associated with them, but as long as you're aware of the risk and they can be monitored, it's manageable. So it's a manageable risk, even though it's not zero. So it is something that is worth considering. But I think it's in terms of our first therapy through the gate and a long time that actually affects the time course of the disease, it's actually pretty good. I mean, 1 to 2% of people that have some serious complications is certainly not zero, and it's something worth worrying about. But especially since we know what to look for and what to monitor for, I think it's something that we can deal with. Now, here's where things get a little bit both dicey and interesting. If you're thinking about these different antibody therapies, remember that aducanumab was super controversial, right? And lecanemab just got approved. And donanemab, the other one that I mentioned, is probably going to get approved later this year. So here's your engage and emerge trials. And if you look at the top one there, that's the actual wing that didn't work. And the other one at the bottom, the emerge one, is the one that did sort of work. And if you're thinking about how much amyloid you need to get out of the brain to demonstrate efficacy, it looks like you need to get rid of nearly all of it. But the rates of these things and how they clear amyloid out of the brain is different. So aducanumab wasn't quite as fast as the other two. So it turned out that the second trial, the one that did have a little bit of efficacy, it had a different time course. It started at a different time, and they changed the dosage a little bit. So it was a little bit more effective at getting the amyloid out of the brain. And that was the one that barely worked, right? But the other two, lecanemab and donanemab, those two actually are much faster and more effective at clearing that amyloid out of the brain. And those ones have a clear clinical benefit. So this is very much telling us that these drugs, there's a relationship between the speed of how they clear the amyloid out of the brain and how well they work at treating the disease, or how much clinical benefit they're going to have. So if you just look at the ones that didn't work, so things like gantenerumab that I mentioned earlier, it's able to clear amyloid out of the brain, but it's very slow. So there's a rate constant over on the side there showing you how fast they are. So 19 is slow. And you'll see at the other two, lecanemab, aducanumab, and donanemab are the other three. They're much faster. And the one that barely worked, aducanumab, had the slowest rate of those three, so 6.4. Whereas the other two, lecanemab is 4.2 and donanemab is 3.6. So I told you these things are a mouthful. I'm going to trip over myself trying to say them. But what you're seeing there is the ones that are removing the amyloid from the brain fastest are the ones that work in that order. So gantenerumab and others don't work, even though they do in some cases clear amyloid from the brain. And then the ones that barely work clear it the slowest, but they seem to still cross some threshold. And then they get better from there. And the final results from that last one will be next week. So I'm sure you'll see news reports on that. Now, don't worry too much about the details here, right? But there does definitely appear to be a time lag. So one of the reasons why we think that our clinical trials have been so mixed on this is that there is a period of time where you need to clear the amyloid from the brain. And you figure there's all this amyloid in the brain, there's inflammation associated with it, and that's driving that tangle pathology later on in the disease process, right? So if that amyloid pathology is removed from the inflammation and the tau from a couple of steps, then after you clear that amyloid away, there's going to take some time to have an impact on the tau pathology and the inflammation and everything else. So of course it's going to take longer. So if you only have a clinical trial that's 18 months long and it takes a year to get the amyloid out of the brain, those people aren't going to be showing a benefit yet, right? It's going to take longer for that to show up. So if you have one that clears all the amyloid out in like 3 months, they're going to start to show a benefit faster. So that's what you're seeing in these trials, is the ones that looked like they didn't work or barely worked before were just too slow. And if it went longer, if the trial went a little bit longer, these would probably work. And that's a cause for a lot of hope, right? So if the length of time treating and the speed of that amyloid removal are really that important, many of the things that we've thought in the past didn't work actually might really work well if we go earlier in the disease process. And that's really where I think we need to be focusing a lot of our effort, because a lot of these drugs that have washed out before are way safer than the monoclonal antibody therapies, and many, many, many times cheaper, right? So you can envision this future where someone might be screened for early AD pathology in their 50s, kind of like now when you would go in and say, oh, you know, you're in your 50s, your early 50s now, it's time for you to get a colonoscopy for screening for colon cancer. And by the way, we typically start screening for Alzheimer's disease pathology now. So you would get a PET scan or a blood test, or in some cases, a lumbar puncture to screen for markers of the disease. And then what you would do is you could do something like, okay, you have a lot of amyloid pathology in the brain. We do an infusion of a monoclonal antibody to clear this out of the brain. Think of it as something like chemotherapy. If you had various forms of cancer, you'd use it to get the amyloid out. Once that amyloid is gone, which you can see by PET scan now, you'd switch over to one of these drugs that you could use for long-term maintenance that are cheaper and safer, and you would keep that amyloid from reappearing in the brain. And you just do follow-ups after that. And if the amyloid starts to show up, you try a different monoclonal antibody infusion to clear it before it starts to do all of that damage in the brain. So I think that we're at a really pivotal point in how we treat and manage the disease going forward. And I think it's really incredible that the persistence that we've had in this over several, the last couple of decades to move this forward. And I think it's pretty safe to say now, I don't think we've proved that amyloid definitely causes the disease, but I think the weight of the evidence is pretty strongly leaning there now. One of the things I think we need to be thinking about is in terms of how we can improve our detection of the disease even better, kind of getting it embedded into the public consciousness that in addition to doing things like getting a colonoscopy in your 50s, you need to have someone figure out if you've got incipient Alzheimer's disease pathology. Because it's pretty realistic now to think that within a very short period of time, we're going to have ways to prevent the disease, maybe not through immunotherapy, but other measures that we can use early in the disease process, that even though they might be slow or too slow to work once you start having cognitive impairment, they can work really well, right, at slowing or preventing the disease. So if you think of something like, analogous to something like cholesterol management, you get a lot less benefit out of reducing your cholesterol once you already have heart disease, right? But it works really well. We're lowering your cholesterol way, way back in your 40s at preventing heart disease. And as we develop other therapies, we can move those things closer and closer to where the onset of clinical symptoms are. So we can, for example, combine A-beta clearing therapies with tau clearing therapies or anti-inflammatories. And then eventually we have to get to that really difficult point down here where how would you repair the damage that's already been done for people who have already got to that stage? That's a really difficult problem. So how would you actually repair that damage? And although theoretically that's something possible that we can do, it's not easy. I mean, replacing those lost neurons is a tough road. But it's not impossible. I mean, there have been really good studies in various mouse models and rat models showing that it can be done, but we're really far away from being able to do that in people now. And I think that is where I could talk all day about Alzheimer's disease, but I need to stop there because I know we don't want to keep you here forever, and we can do some Q&A.
I think the real takeaway that I got from this is really like with Parkinson's, the early identification of markers is saying who is at risk, not only after you've looked at the statistical side of it, but then instituting the incipient therapies, the preemptive therapies, and then the maintenance therapies. But you probably will never really get to the reparative therapies. Is that accurate?
Yeah, I mean, that's currently where we stand. I don't think it's impossible to get to the reparative therapy, but it's certainly difficult. I mean, there have been years of promising work in things like stem cell therapies, and that hasn't even gotten to the stage where it could benefit Parkinson's patients a lot. And you would think for Parkinson's patients, where a lot of the damage is in the substantia nigra, so it's a lot of the key driver of that disease process is damage to an anatomical structure in the brainstem. And you think that should be something that should be easier to repair. So we'll probably see demonstration of a benefit to Parkinson's patients in terms of repair way before we see an Alzheimer's one, but we're not anywhere close to that yet. I mean, that's going to take a long time. I think at this point, even if you can catch someone even at early stage mild cognitive impairment and you can stop the disease from progressing, that's a huge advance. Because I mean, people can live with mild memory loss, right? And that's I think where we should be aiming for first.
So we're still toddlers. We're not running 50-yard dashes.
Yeah. But I mean, we've gotten so good at early detection now. I mean, I think there's a lot of hope there, that especially people where Alzheimer's runs in their families. I mean, if we have therapies that will slow the disease, and you can tell people in their 50s that, yep, we're going to screen you for Alzheimer's disease pathology in your 50s, and we have ways to slow it down. It didn't matter so much when we didn't have anything that could slow the disease, because it's like, well, why get screened for it? There's nothing you can do. But if there's a way you can detect it and slow it down, then it becomes incredibly important.
Is the APOE marker the best marker that you have to date for genetic risk?
For genetic risk, it's the strongest one. There's a lot of other ones. APOE is as close as you can get to something that will tell you if you're almost certain to get Alzheimer's disease. If you're APOE4 homozygous, if you have 2 copies of that allele, which is about 1 in 5 Americans have 2 copies of that. Then what you end up having is, I think when you get to your mid 80s, you have about a 50-50 chance of getting Alzheimer's disease. So it's a very strong risk factor. And even having 1 copy of it, it's about 20% risk, which is still pretty high. It's 1 in 5, right? And that's one of the concerns with the monoclonal antibodies, because when we're looking at efficacy, it looks like they don't work so well on APOE4 carriers. And part of that, it's really hard to kind of nail that down, because a lot of times if you think about, well, you have this risk factor. So if the way these things work is how well they clear that amyloid pathology out of the brain, people that tend to have these risk factors tend to have more aggressive pathology anyway. So it's a case of like, well, maybe if you caught those people, since they have high risk and you could screen for them earlier, if you treated them early, they would be fine, right? But just by the time they show up with clinical symptoms, they have so much pathology already, it's really hard to get rid of it in time to make a difference.
Dr. Murphy, I think a lot of folks are interested in that concept that you shared of the early screening process and relating it to the colonoscopy. I think we all can associate with that. And so one of the questions in the chat is that reasonable now to be screened at the age of 55 or in our 50s? And if so, what type of facility would one visit? Who would they call to do something like that?
So here's the thing with screening. So there are several FDA approved screening methods, but none of them are covered by insurance. So this is something that really I think needs to change, especially now that we have some therapies, right? Right now you can get any of those screening things are done at academic medical centers where there's an Alzheimer's center. So University of Kentucky has one, but there's a lot of them throughout the country. I think there might be 40 now, but there used to only be 30. So the issue there is accessibility, and a lot of people are just not they're not close enough to one of them to get that sort of screening done. There has been some significant movement in developing both CSF, so cerebral spinal fluid markers for Alzheimer's disease, as well as blood markers. They're not quite there yet, but they're getting close. I mean, one of our long-term goals as a field has been to get a blood test for it, because then you could just go to any doctor and they could just send out the blood work and they could screen for it. We're not quite there yet. We're actually nearly there for CSF markers. So in that case, you would still have to get a spinal tap, which sucks. I don't know if any of you ever had a spinal tap. Not nearly as bad as it used to be. With one of our neurologists here, Greg, who runs a lot of our clinical trials, he actually has a YouTube video where he has one of his residents does the spinal tap on him. So you can say, see, look, it's nothing. It's totally fine. So you can tell people it's something doable. The risk is relatively low these days. But I think, by and large, unless you're a really unusual person, you really don't want to have a spinal tap. So a blood test would be much better. So getting screened is something we need to work on in terms of expanding access and having more people able to get there. Right now, you need to have somewhere with a good PET scan capability.
There's also a question there about the average length of time for what you define as early stage. Can you talk about that for a moment?
So that depends where you're going to put the marker. So if you're talking about from the time someone has mild cognitive impairment and then has amyloid pathology, that's what we call amnestic mild cognitive impairment. And that's kind of the earliest stage of what you would consider to be actual Alzheimer's disease. And from that point on, you've got the decline varies a bit, but from there until they pass away, it's like anywhere from 5 to 15 years, right? But the decline typically from mild cognitive impairment to full-on Alzheimer's disease is maybe 5 to 10 years. So if you're thinking about how long, in terms of how long is the pathology around before people start to have symptoms, that's quite long. It seems to be about 15 to 20 years. So most people, the thinking is now that most people who are going to get Alzheimer's disease have amyloid pathology sometime in their 50s. So they could actually see it on a PET scan in their 50s or at least early 60s. And that's a long time before you actually symptomatic. So remember, the symptoms of the disease are showing up when you have neuron loss, right? So once you start to have losing neurons and synapses in the brain, that's really what you're losing your memory from, right? It's those loss of cells. So if you can get rid of that amyloid pathology before it causes a lot of inflammation, before there's lots of tangle pathology, before neurons start to die, you should be able to prevent the disease. And that's a long lag. It's like 20 years. I think the biggest concern with that is if it's something like, oh, it's 20 years. It's like, well, those monoclonal antibodies cost about $26,000 a year. So it's like, are you going to, if you don't have insurance, you can't pay for that, right? And that's a lot of money. I mean, if you had to get that continuously for 20 years and it's infused, I mean, that's not pleasant. I mean, if you have to get those antibodies infused every 2 weeks to a month for decades, I mean, that's not good. So that's why I think being able to clear it out and then have a maintenance type therapy is really the way to go. The thing about those monoclonal antibodies too is I don't really see them getting much cheaper. That's the problem with those. They're just difficult to manufacture, and it's just there's a lot of built-in cost limitations. I mean, there's obviously problems in the UK and the US's healthcare system in terms of price controls and things like that as well. But I mean, they're still never going to be really cheap.
Yeah, my wife was 50 in 1999 when she was diagnosed, and I took care of her for 11 years. For the first 4 years, I had no insurance. It cost me over $150,000 because the doctors kept fighting me on the fact that she was so young, they would not look at Alzheimer's. They went every which way. So I finally had to have a neuropsychologist test her. And then the state had to test her and say that she had Alzheimer's before I could get any help. Well, there's 16 million caregivers out there, and 40% of them are dying because of the stress. But there doesn't seem to be. I tried to get her into 3 clinical trials. They did cognitive skill testing, and she failed. The stress on the caregivers. And you're talking about prolonging that process. What does that do to the caregivers, doctor?
Caregiver burden is a huge issue. I mean, the Alzheimer's Association puts a significant amount of effort into ways to address caregiver stress. So if you are able to stop progression of the disease and manage it, the caregiver burden will be much less, right? Because you're not going to be dealing with this rapid or progressive decline over time, right? The idea here is if we can stop the progression or slow it down so much that it's no longer perceptible, then the caregiver stress will be more manageable, right? Because it's not going to be a significant burden. It's definitely a worry, though. I mean, you don't want to have something where if the disease continues to still progress, and then the person is going to last for 25 years instead of 12 years. I mean, that's a concern. You don't want that situation, right? But I think we can probably, hopefully, avoid that going forward. I see one more comment that I can comment on about lifestyle, diet, exercise, brain exercise as a way to prevent Alzheimer's disease. The answer is definitely yes. It's what we always tell people in terms of your best way to prevent AD is being generally healthy. And that covers just about everything you would do to be generally healthy. Eat well, exercise, both mental and physical, have good social contacts, join like the Rotary Club. Yeah.
Excellent. And do Wordle every morning, right?
That should help.
Absolutely. Dr. Murphy, thank you so much for being with us today. This is it's been an incredible opportunity for us to hear directly from you, and we will share this on our social media. So please follow us on Twitter and on Facebook as well. And don't forget to check the calendar on the CART Fund website, because it will have all of the dates of these future meetings and all of our other meetings that everyone is invited to attend.